Okay, so first questions here come with constant head permeability test setting with specimen length of 200 millimeters. We know the cross-sectional area is 78.5 centimeters square. And it also provides the hydraulic conductivities equals to 2.1 times 10 to negative 2 centimeter per second. It's known that there's a weight comes in and goes out the specimens. So it's a constant head test. So we've got a water reservoir there, a huge reservoir here that the water level won't change throughout the test, and the reservoir connected to the bottom of the specimens, and then come out from the top. So come out from the top, the water come out from the top freely. You go in the bottoms, come out from the top. The weight that go in the soil specimens is 130 centimeter cube per minute. And now the question asks, what is the head difference? So what is the head applied to the soil sample? So this is the picture for the questions, and it's a constant head test, and we record our FE menu. When you see the constant head test, the keywords in the FE questions, when you go back to the FE menus, think of this equations. It helps you to get started. So it gives you the K values equals to the capital Q divided by I times A and T, and realize that this capital Q means the volumes, and the time here gives you the dimensions of hours, seconds, or minutes. So you have a volumes developed by the time. In fact, this is the weight. So the weight that goes into the soil specimens is given. So if we organize these equations, then we got this. Again, we start from the FE menu equations, and then given what is provided, then we got this equations right there. And we know that we are being asked to solve for the delta H, and we don't have a delta H in these equations, but we understand that again from the FE menus, the delta H is the DH right there is pretty much related to the hydraulic gradients, and which is part of the equations. So we can solve for the hydraulic gradients. So this is Q equals to K, the I equals to the Q divided by K times the area. So if we plug in the informations right there, we know the rate. We also given the hydraulic conductivities. It's a reciprocal, so we split the units, and also the area, and we take care of the units, because now we have the given the seconds, and also we have the seconds and the minutes over there, so we take care of the units. And realize the unit cut cancel out. And hydraulic gradients is a dimensionless parameters. So eventually we got this I equals 1.314. So with that, we can solve for the head, because we know like from FE menu, the gradients equals to DL, and pretty much is the head difference here now, divided by the length of the specimens. So this is the length of the specimens, and this is what we want to solve for. So the delta H will be equals to the gradients times the length, which is equals to 1.314 times the 200 millimeters. So the head applied across the specimens is equals to 26.287 centimeter. Okay, question number 2 is also a constant head test setting. So this time we have cylindrical specimens of 6-inch long, diameters of 3-inch. And again, it's a constant head test setup. So we have a reservoir here with a lot of water. And the reservoir is connected to our spoil specimen again, and then come up from the top. Connect to the bottom and then come up from the top. Given the height of the water that at the infolds and is 5 inches above the outfold. So the head to the where the water come out freely at another osmotic pressure here is 5 inches. And the quantity of water flowing through the water samples is 0.061 cubic inch in 8 hours. So we have a graduate cylinder here to collect the amount of water that come out. And the water there, we collect this 0.061 inches crib in 8 hours. So the times is given as for the test durations is 8 hours. So now let's ask what is the hydroconductivities of the tested soil sample here. This is the soil sample. And this is the water collected. Okay, so this is a constant head test, and again, referring to our FE manuals, we look at the hydraulic conductivities, and for the constant head test, and we are aware of this formula. So you always, every exams, finding the right information is the correct formulas always give you a head start. So that formula is K equals to the capital Q divided by A times T. So we are solving for K, and we realize that pretty much we have all other informations. We have the capital Q, we know the time, we know the area, and now it's only the gradients. And the gradients is are going to, for FE manuals again, is DHDL. Which is equals to our head here, which is 5 inches. So the head applying to the specimens coming from the bottoms and then coming from the tops, and the length that you travel through is the height of the source specimens. So with this informations, then we can solve for the gradients. So pretty much we have all the informations. So the K equals to the capital Q, so it's 0.061 inch cubic, and then the I is 0.833, and the area we can calculate that, which is the specimen area, cross-sectional area, which is equals to pi r squared, and we know the radius, which is 3 inches divided by 2, and then the time now is given as 8 hours. So we do our math here, and we can solve for our hydraulic conductivities. Will be equals to 0.001 inch per hour. Okay, question number 3. This time is a falling head test. So is testing a falling head testing on a specimens with length of 15.24 centimeter. The diameter given is 7.62 centimeter. And the hydraulic conductivity of the soil samples is known, which is 0.048 millimeters per hour. And this is a constant, a falling head test. So you just connect it to the soil specimens again from the bottoms with a pipette or stem piped right here. So connect to the bottoms, and then again, assume the water come out from the top freely for the drain gauge. And initially, the water level is 1 meter above the top of the soil samples where the water comes out. So this is the initial water head. And then like after the end of the test, the water level fall, and then it just drop by. So this is later on. The water level is dropped by 20 centimeters. So from top, beginning of the test, the water level, and after a certain time, the water level dropped 20 centimeters. So that's the set of the test. It's also given that the area, the cross-sectional area of the pipette is 0.2 centimeters square. And now the questions ask how long did the test last? So how long it takes for the water level drop by 20 centimeters, given the soil specimen dimensions and also the hydraulic conductivities. So since this is a falling head test, so again, during our FE exams, you have your FE manuals, and always good that you identify what equations helps you for your FE test. So falling head test, we consider this formula here. And again, for the derivations of this formula for both the constant head and also falling head test, you can refer to my other videos, which the link is provided in the descriptions below. I walk you through how to come up with those two formulas, and also have more like other YouTube links to go to the lab in the lab setting, walk you through how the laboratory is set up for the falling head and also constant head tests. Okay, now we know the formula. The formula is K equals to 2.303 times the small area from the stem pipes times the length of the samples divided by the area of the samples times the times, and times the log of the head drops. Actually, it's the ratios of the initial height and also before test height, water height, and also after test, what is the water level height with respect to the water drinkage come out from the top of the specimens. So H1 and H2. So pretty much this one is your H1. So this is your H1. And this is your H2 right there. So H2 will be equals to the 1 meter, which is 100 centimeters, minus the 20 centimeters. So the 20 centimeters belongs to the waterfall during the test. So H2 will be equals to 80 centimeters, while H1 is the 1 meter, which is equals to the 100 centimeters. So if we go back to equations, and again, what we are solving for now is the time. Because the question asks, how long did the test take? So pretty much we are solving for the time right there. And we reorganize the equations because we solve for the time. So we change the equations, we organize it, and realize pretty much we have all the parameters that we need. It's always good to keep track with the units. So it helps you to eliminate any potential mistake, especially like, during the exam. So the length of this examples is 15.24 centimeters. So this is the length of the specimens, and divided by the area. We can find out the area of the specimen. So this is the area. This is just given the diameters. So pi r square again, the circular area. Check with the units. And also we are given the hydraulic conductivities. And the good thing about keep tracking the unit is we realize any units conversions we need to do, and we can do it properly. So we keep track of the units, and we realize that the units cancel out, and left with like the units that we need to solve for, which is the time, hours in this case. And don't forget also the log of H1 and H2. So we mentioned previously H1 here is the initial water height, so which is 100 centimeters, and the H2 is the after test, at the end of the test, which is the water height. So with that, we plug in the informations. We got the solve for the time. We find the time is about for 3 hours. Okay, so question 4 here is solving for you have a site where you have a dam sitting on a fine sand, saturated fine sand deposit. So and the dimensions of the dam and also the water level from upstream and downstream are given to you. And also a full net has already been constructed. And you are being asked by 2 questions here. First, calculate the flow of water through the site, and also find the factor of safety against seepage liquefactions. And for the fine sand, so this is a fine sand site. The soil properties are given to you. We know for the sand, it has a water content of 36%, and specific gravity of 2.7, and the hydraulic conductivities is equals to 3.5 times 10 to -4, so typical sand range right there for hydraulic conductivities. So all these informations are given. Now you ask what is the flow of water in terms of centimeters squared per minute. First, so we find the amount of flow rate through the sand deposit, given like we have a geostructure, a dam sitting on top of it. So we want to solve what is the flow rate from the upstream to the downstream. And you start with when we are given a flow net and ask the flow rate. We start from equations of this one. So the N sub F there is the number of flow tubes, which is given by the flow net. So what is a flow tube? Flow tube is what you can see here. This is one flow tube. This is the second flow tube. Oops. And this is the third flow tubes. So we have 3 flow tubes. And next, N sub D. What is N sub D? N sub D is the number of drops. So N sub D of so number of drops on each flow tubes. So we find, for example, we have 1 flow tubes here. We have 1 drops, 2 drops, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 drops. So N sub D equals to 10. So both N sub F and N sub D, those are the parameters for the flow net. Once you construct a flow net, and very likely in FE exams, if you see a flow net problems, because of the time constraint, the flow nets were already given to you. Now it just comes to a matter that whether you know how to count N sub F and N sub D. So N sub F is the number of flow tubes, and N sub D is the number of jobs. So this case, N sub F is equal to 3, and N sub D is equal to 10. And K is given, which is the hydraulic conductivities of the soil. So the flow nets problems likely as FE level will be assumed to be you have a homogeneous site. In this case, you are given of a constant hydraulic conductivities, and the delta H is the head difference between upstream and downstream. In this case, you are given like the upstream water level is right here, and the downstream water level is there, and the difference is different at 6.3 meter. So pretty much now we have all the information we need for the equations. So you plug it back. So N sub F is equals to 3, N sub D equals to 10. And again, keep track with all the units. Per seconds, and the height is 6.3 meters. And we want to express our answer in terms of centimeters and minutes. So we do our unit conversions there. So we multiply that by 100 centimeter per meter square, and then changes to minutes. So 16 seconds per 1 minute. And we realize the units cancel out. So it's very important to check ourselves that we eventually get to the units we want. So at the end of the day, our answer given is about 4 centimeters squared per minute. Okay, next is being asked what is the factor of safety against seepage liquefactions. So when we see those keywords we go back to our FE manuals, we find these equations right here. So that's the equations that we will use. So solving for the second part of the problems. So part B, right there, is find the effective safety for Seepage liquefactions. So the factor of safety given is equals to I sub C divided by I sub E. And I sub C from the FE manual is further given by these equations. And the I sub E is the exit gradients. We'll talk about how to find that. For the gamma saturated, if we go back to our FE manuals again, from the phase relationships problems, we are given by these equations. So the gamma saturated is equals to G sub S plus the void ratios times the gamma water divided by 1 plus E. So the G sub S is given, but like we don't know about the void ratios. And we call that there's a famous equations. The George Washington is a soil engineer. So every time like you are being asked the void ratios, ask yourself whether you know like the G sub S and also the water content, and whether the site is also fully saturated. If so, then the void ratios will be equals to the specific gravity times the water content, which is our case. It's a fully saturated sand site and also given the G sub S and the water content. So, but these equations you can also find in the FE manuals. Which is these equations here. And we plug in the informations. So our void ratios equals to the G sub S, which is 2.7, times our water content, which is 36%, and divided by the saturations, fully saturated, so it's equals to 1. And our void ratios is 0.972. So we put in the informations in this formula. The G sub S is 2.7 plus the void ratio 0.972 times the unit weight of water, which is 9.81 kilonewtons per meter cube, and then divide by 1 plus the void ratios. And we find the saturated unit weight, this case to be 18.27 kilonewtons per meter cube. So we can calculate the I sub C now, which is equals to 18.27 minus the unit weight of water divided by the unit weight of water. And we find the I sub C equals to 0.662. So next, we need to find out the exit gradients. And what does it mean by exit gradient? For this site, which we are talking about, is the gradients of this particular box, or this grid right here. So on this grid, we can find out the gradients, because we know like now like we have heads. So we want to find out the change of water heads in this grid, which means like for the water head entering this equipotential line, to exiting this equipotential line. So which is like for the case that like entering and exiting. And the delta H for that case is the total amount of water heads across the site divided by the number of jobs. So essentially what it means is like the whole site has water heads of 6.3 meters, and this is shared equally by each drops, and it has 10 drops, the ends up D. So each water grids right there, water flow net grids right there, share the same amount of energy. So at the end of the day is the total heads that we have across the site divided by the number of drops. So this case is 6.3 meters divided by ends up D, which is 10, equals to 0.63 meters. So this represents each water head drops per the full net grid. And in order to find the gradients, again, it's like we want to find excess gradients. So we want to know the head drop across the distance that it traveled, which is this distance here. Oops. This distance here, which is like this from the full net, we can measure it. So if you have everything draw on scales, we can find out the distance representing like this particular full net, the length of this grid. Essentially, it's like how the water travel through this grid. And the distance here now we assume it is 1 meter. So this DL is equals to 1 meter. If you have FE exam questions, this dimensions very likely is given to you. If you construct the full net yourself, you can measure this distance according to the scale of your drawings. So with that, we know our exit gradients will be equals to the delta to where FE formula is the H divided by DL, and this case is the delta H we talk about, the head drop of each grid divided by the dimensions of the grid. So which is 0.63 meters divided by 1 meters. So this is 0.63. So gradients again is a dimensionless parameters. And at the end of the day, we go back to our original equations right there. So F vector safety for seepage liquefactions equals to I sub C. We calculate 0.862 divided by the I sub E, the excess gradient, which is 0.63. We plug in number, we get 1.4 for our vector safety against seepage liquefactions.